ask you pertaining to manufacturing, pertaining to raw material, and thereby this talk will be more general and to just update you superficially what are different manufacturing methodologies are there as far as additive manufacturing is concerned, where we are talking much about 3D printing. So if you look at this slide, except this, cycle one, I think others are much more familiar to you. Now here I'll mention more about this essential one. This what it shows is industry is not required. What I mean by industry is, as Professor Nikhil has mentioned, that when we go for a conventional manufacturing, we need a casting, we take the molten metal, we pour it, but the issue is we always get a similar size dimensions. So as against in medical field or dentistry and so on and so forth, we have a different geometry. It's a specific geometry where if we need to follow the conventional methodology, you'll end up paying almost 100,000 times more because we had to repeat that process altogether. But in case of 3D printing or additive manufacturing, in that sense, we can have a customized product. You can have your own design for a mobile cover. You might want to print with your name, and that's possible, and you do not have to depend for an industry to supply you material at high cost. So if you have a printer like that, you just have your own design and get it custom made as per your thinking and usage. And from this we can have custom made cycles to further to medical applications based on the geometry. Patient-specific things we can always print. So here, the manufacturing has become more local now. It is in-house manufacturing, on-the-go manufacturing, not only in terms of medical field. Let us say we have a soldier fighting in Siachen, and he has a rifle wherein the knob stops working, but he had to perform a duty. But if, in that case, if he has such 3D printers and he has a drawing, he can print it then and then itself and put it and start executing his duty without any delay. So this additive manufacturing is touching each and everybody's life, including the medical, which is most complex, because in case of mechanical components, it is more or less standardized. So if I say AK-47 or so and so forth, I have components of a standard dimension. But when we talk about medical field, things are more complex because geometry is continuously varying. Now when the geometry is continuously varying, in manufacturing segment, we have many issues to be addressed, how we can replicate that geometry to exactly come down to what is required. Yeah, fine. So what we need basically in additive manufacturing is a printer, that's what you're seeing here, and then a raw material and a system. Now raw material, we have certain limitations right now. So there is much more material innovation going on. I'll tell you of the examples which might be close to the medicine fields. So we have right now certain limitations on the raw materials which can be handled by this printer. We need a system to digitize it, as Professor Gupta was mentioning. We need to convert it to go to the CAD model and then slice it and move further. Fine. So this is a typical additive manufacturing process chain. Earlier speaker has elaborately discussed about this. So we start with a CAD model, computer-aided drawing, and then we convert it to a steel format, that is stereolithographic format, and this is most common format because here slicing is easy and many software packages are convergent with this STL format. Therefore all of us, we always talk about an STL format. Then we send it to a system, set the parameters. Now here is a major thing as an engineer comes in picture when you want the part to get printed. Now there are many parameters. It is not just like you give a printer, you give a command and just get the product. But once you get the product, it should be, as the speaker has mentioned, has to have with good properties. Because this element, if I talk about a medical field, is going to take different loads. If I am fitting it here, as part of the leg, there are different types of load acting. But to take a simple example, if I'm standing, there's a static load acting on that. If I start walking, the load rate changes. And suddenly if I start jogging, magnifies. Running goes to peak. So thereby, the same element has to come across such large load variations. And if your printed component don't have the capability to sustain these variations of load, then it is really going to be a worst component to be printed. So thereby, in manufacturing perspective, we need to take care of a lot of many things, and we set the parameters here based on what load is acting. If we go to the implant, then if you are putting inside the body, then how it is going to react with the body fluid. Can we develop a biodegradable implant? Yes, there is a solution, there is a material, but can it be printed? Can it give the same properties as you graft the bone there? So there are manufacturing a lot of challenges whenever we talk about that. And thereby we have certain material limitations based on the manufacturing processes. I take a simple two examples here to just show how part can be accomplished. Now, if I just look around, if we like just look around this component, there is a thin plate, fine. There are pores, smaller ones, larger ones, but one thing we need to understand here is, if you look of any of this geometry, it is repetitive in nature. What I mean to say by this is, I hope all of us know the honeycomb, right? Do we know honeycomb? Yes. So it's a repetitive pattern. Meaning when I'm printing, I can print a repetitive pattern. Or in other words, can I print a cone? Yes, to a certain extent. Can I print a sphere? Not right now. Because we need a support material based on, again, different manufacturing methodologies. It will go ahead. So the issue to mention here is 3D printing, yes, we can print it. What pattern you want? Because if I look around typically a bone has inbuilt porosity. Now can I replicate bone exactly? So that depends on what texture it has. To other side, this is a repetitive pattern which we build layer by layer. I hope all of us know the sponge, the scratch bar used in the kitchen. Right? A typical sponge has also the pores like this, but those are not repetitive. Those are interconnected. So if you say, can I print a sponge? Right now, I say no. Because there are challenges to exactly replicate those things. Because when I print one layer onto the other layer, the second layer takes the support of the first layer. I can offset it, but to a certain extent. So thereby, we have the issues related to replicating the natural pattern. Likewise here, we can have different texture changes too, and that is again, if you see, it's a repetitive in nature. So yes, to a certain extent, we can replicate some of the natural things which you want, but many times, no. So what we do here in CAD modeling, the basic consideration, when you say, can I print this, we need to look for this. Thin walls, do you have? Small pools, porous scaffolds. I think this is again related to, very close to your arena. Now when we say porous scaffolds, how much porosity, how much small hole I can print? Again, that depends on the machine, what you're going to use. What's the resolution, what's the speed, how the thickness is going to vary, and so on and so forth. So when you say, when we look at the structure, we decide based on this which manufacturing is done. When you are doing a 3D reconstruction, when you take a CT scan, I think there might be some other elements also, because I don't know medical terms much. So there might be some other elements also wherein there might be a overlap, which I am not interested to. So thereby we need to selectively eliminate those using, there are many open source softwares, or there are other softwares too. There is a 3D slicer, we slice it, during slicing we model it and just look around which part to be focused, and then we remove it. So that we look into this, then build the 3D model, and then finally print. Please do remember, why there is much challenge in case of medical field is, if I look at this structure, the geometry is continuously changing. We cannot exactly replicate what your CT scan gives us to us. I'll tell the reason for that. We are close to minimize that effect, but still not exactly. So we'll be closer enough with some tolerances. So here, when we build it, then as before sending it to the printer, what I need to look for is if there are any missing facets, if there are any overlaps. So we need to just rectify it, because 3D printer will understand only the file which you send. As a person who is operating in this manufacturing industry, which is in-house, on your desk, on your desk, we need to look for what are to be illuminated, what is required, what is of interest, point of interest to us. So that we need to do, we need to find out, and then we have EM system, additive manufacturing system constraints too, pertaining to shrinkage, distortion and post-processing. Shrinkage meaning reduction in size. Because when you are converting a phase of a material from liquid to solid, solid through liquid, again back to solid, there are phase changes. So the dimensions shrink. What material you are looking for, if you say beta tricalcium phosphate, that's what Dr. Khader was mentioning, I want to really know the chemistry of that material. That material has to be available as a raw material, number one. Then I can go for 3D printing. Whether it is available in the liquid form, whether it is available in the powder form. If it is in the powder form, what is the particle diameter? Because all these things determine the thickness of the walls if you want to pour a scaffold. And that limits the manufacturing in that sense. So shrinkage we need to take care of. We need to optimize a whole lot of process. There are 3D printers available which use some qualified materials for which they have done the optimization. But if you want to try out the new different material, we need to do all this optimization to just address the distortion minimization, shrinkage minimization, and all stuff. There are a few more issues which, before sending the file to the 3D printer, we need to take care of. Part implementation and support. There are many additive manufacturing processes wherein we don't require any support structure like this. So this is a component, you can print it like this, or even you can orientate it like this. But when you orientate it, you need to go for this much additional support material system. Now when you go for such inclination, your build time increases. So instead of getting this component in 10 minutes, you'll be lining up with 20 minutes. So we try to minimize this support systems if we can, and we try to build it on the base plate straight away so that I can just pick it up and use it. Later, these orientations also determine the properties. Because when I have an inclination for the component to be printed, the nozzle has to traverse many layers. And these will in turn determine the mechanical anisotropy. The properties are different in different directions. So we cannot really going to get the same property homogeneously all around. So these issues we need to answer. And then this was one more slide which I was talking about. In medical, as we have continuous geometrical changes, I said we exactly cannot replicate in 3D printer. The reason is this. Now in 3D printing, we do layer by layer deposition. Now when we do layer by layer, the distance between this and this, and just like two rails, guideways are going parallelly. Now why we need this flexibility? We talked about porous scaffolds sometime back in the earlier slide. So when you want a porous scaffold, I need to have this flexibility of depositing at the different distances. How close I can deposit it, how fine is the thickness of this deposit is determined by the machine capability, nothing but your nozzle diameter. There are machines up to 1 micron, 10 micron, 0.6 mm, 3 mm, so that depends on the nozzle diameter and all the internal processing parameters. So based on what porosity you want, we need to have flexibility that will be printed. And that we take care of that we take care. And this deposition part typically determines the part strength, build time and surface finish. Surface finish typically comes with your deposition angle, part strength comes from how these are being deposited. We can deposit even at an end like this. But if I draw a diagonal here from this to this, the portion of this deposit which is moving from this point to this point is unsupported. If I draw just a diagonal here, because there is no material below to support it. So this is where the mechanical property needs to be adjusted to the core. And here is what is the weakness, because there is no material supporting below. And thereby we say repetitive pattern is printed perfectly, and those have better properties than others. How many we can print? Based on, you have a printer here, the plate size. So we try to print more. We can print of different thicknesses, but preferable is you print many components. Let us say you need to print teeth, 25 teeth of the same dimensions, so that you can have efficiency in better time. But nevertheless, you can print different heights too. You can print different thicknesses, different heights at the same time. But it requires time. So this is typically a metal 3D printer. So we need to optimize that build layout. Then the part building, smaller to larger. So volume determines whether it is going to be printed in few hours or a day or a week. This is typical titanium tip stem. You can just, I think visually we can easily make it out that this surface is smooth and this is having some different texture. Now, AM machine has to have the capability of putting that. So what I need here, as per the earlier slide, this one, we can replicate at the local regions too. In case of conventional methodology, what used to happen is after casting, forging, we used to go for a specific coating for having such structures to be printed. But in 3D printing, you can get it done in a go for a specific system. We can go for a smaller holes or a larger holes, even a larger volumes. What happens once after getting print done? We say that post-processing is not required as like a conventional methodology. It is not so, it is required, but the lead time or the time for which we used to do the post-processing is substantially reduced here. And there are methods for which it is required for all the cases. Cleaning. So if you have a powder base, which you have built, we need to clean up the powder. If you are using a liquid additive manufacturing, you are getting it much earlier. So if I talk about lead time, it is reduced almost by 1/4, and you need not have to depend on a company which is manufacturing it. You have a 3D printer, print it here, and have it at your disposal. So here, in case of additive manufacturing, we have faster processing, cost-effective manufacturing, because here we have lesser number of processing steps, and we are not removing any material. In conventional methodology, we are removing the material. It is just like you eat ice cream. So what the ice cream fellow does when you want a scoop is, he scoops out. So from the existing vessel of a material, he scoops out some material. So that's what we do in subtractive or conventional manufacturing. But in additive manufacturing, I go on building it. So here, material wastage is less, and I can go very close to what you require. And that's how the lead time is substantially reduced. And that's what we mean by significant reduction in material system. Okay. Nothing is green on the other side of AM. There are some challenges to be addressed in AM. So we have a poor surface finish for all the AM manufactured components. So we need to make it smooth. It uses the sanding system, then slower build rates, because there are some material systems, especially in metals, those are more reactive. So I need to have a complete argon atmosphere within which I need to print it, I need to evacuate, I need to purge the new one and purge the gases so that it will be more controlled environment, and thereby the build rate goes down, higher printer costs from 9,000 up to 5 crores. So when I say 9,000, we have certain limitations of what part I can print size-wise, what material I can use. So we typically use ABS. If I want to use PEEK, nylon, 120 or even 90 degrees will not suffice. So I need to change the system, go for a higher one. So there are two basically streams. One is a polymer 3D printer, which is available from 9,000 to up to 1 crore. So when I talk about 1 crore polymer system, it is having a large build size. So what I mean by build size, I can print in 1 crore system 2 cubic meter block. So larger components. So typically we go for those printers when we need aerospace applications. We go for a smaller size, midway size, when we are going for orthopedic implants or something related to that. For dental ones, most probably will still settle down. In case of metal, the process is more complex. So in case of metal 3D printers, it will start from 1.5 crore up to 5 crores based on what material you are using. Again, there are some material limitations in metal 3D printers, which I'll talk a little bit later. So we have the issues which need to address. Yeah. So I'll just give an overview about what are these additive manufacturing technologies. The first one is photopolymerization. Here we need a material in the liquid form. As against powder bed fusion, wherein the raw material is required in the powder form. Similar is for binder jetting and material jetting. So if you say, can I print TCP, I'll ask which form it is. If it's a powder form, I'll look for this, this or this. These are 3 available options for me as per this one. But if it's a liquid resin, surely we'll go with photopolymerization. Now, compared to these two systems, these two are slower. So your lead time is more. You might get a component here, after 5 hours here, I can get within 1 hour. The reason is the speed with which this laser or photovoltaic source can be moved over a liquid or over a powder system. Typical materials which we can go for is any plastic, metal, ceramic powders, and even sand. For this liquid resin, which is UV curable, we have binder jetting, wherein we spray, typically in common layman's language, we spray glue. So you want to build a cylinder, a hollow cylinder, the glue will spread over to the periphery of, or the diametrical points of a cylinder, and then we have one more fresh layer of powder which will glue to the bottom layer. Again, one more layer of glue is spread, and we just go on building, and we get this binder jetting done. But the issue with the binder jetting is the components are not so dense, because here it is just a gluing effect, and later we need to take the binder out, because binder is the weakest element, because there is no presence of a parent metal as this powder has in that zone. So similarly for material jetting, when it is used for polymers and waxes, so we spray this wax after converting it into a liquid form. There are 3 more, like lamination. So if your material is available in the form of a sheet, we'll go for this technique. Principle remains same. We use a laser beam, a heat source, to just selectively fuse it and make the component to be built in. Then this is FDM, which right now you're seeing here. So here we have a filament which will be taken up in this extruder. Extruder will take it, make it semi-viscous, and then spray it as per your CAD drawing. Here there are different types of polymers available in the filament form, and that can be printed. So if your material which need to be printed is available in the polymer form, yes, we can available in the filament form, definitely we can go ahead directly with this route. If it is available in the powder form, we'll go with some other routes as mentioned in the previous slide. Then we have direct energy deposition. This is typically a metal design. So I was talking about 1.5 crores to 5 crores to 6 crores. It is this region. How the cost changes based on the build volume. So if I'm talking about 1.5 crore metallic system, it is 90 millimeters by 90 millimeters I can print. But when I go on a higher side, I can go up to 250 millimeters by 250 millimeters by 250 millimeters. Still higher, the cost goes up. So we can have multi-axis deposition, like this wrist have lot of number of degrees of freedom. I can make this laser source to rotate, or even the table onto which it is deposited to rotate, so that the deposition is exactly perpendicular and makes a good structure. High surface finish is possible based on the powder geometry, powder chemistry. Final powder will definitely give you high surface finish, dimensional accuracy. All these current AIM printers are having this. Most important, one more feature from mechanical perspective is repair. Now, let us say we have a jet engine, and in engine we have blades. Actually, the engine which makes the flight to fly. Now, let us imagine a case that there is one blade which got chipped off in its service life, or there is a damage. Now, in conventional methodology, what we do, we take this entire assembly down, we take the impaler, we take the blade, and then we replace this entire system, which will take me months. In comparison,